So this is the Honors Chemistry Section 4.2 lesson video. And so we're going to dive a little deeper into the parts of the atom and kind of what an atom looks like was actually discovered. Since we couldn't see one, we kind of had to do experiments and things like that to determine what an atom actually looks like. So three kinds of subatomic particles are electrons, protons, and neutrons. So hopefully you're familiar with all of those before you step foot in my class. Particles with the same charge repel one another. So like two positives would repel, two negatives would repel. Whereas particles with opposite charges attract one another. So like a proton and an electron, because one's positive and one's negative, they would attract one another. So these are just some things you need to know about protons, electrons, and neutrons. So first is the symbol. The electron is just E with a negative, proton's P positive, neutron is N with a little zero. That's because those are the charges. So an electron has a -1 charge, a proton has a +1 charge, and a neutron has a neutral charge or a zero charge. The relative mass is not the actual mass. Okay, the actual mass of protons, neutrons, and electrons is way less than 1. But it's saying that if we set a proton at a mass of 1, that's why we say it's relative. If the proton has a mass of 1, then a neutron also has a mass of about 1. So in other words, what they're saying is a proton and neutron have about the same mass. Whereas an electron would be 1 over 1840. So in other words, an electron is much, much lower in mass. So that's why when we start talking about mass number for atoms, we don't include the electrons. They're so small, it'd be like if I weighed myself and I stepped off the scale and grabbed a couple of paper clips and then weighed myself again. Because I have so much more mass than those few paper clips, the scale is going to say the same thing. Okay, because it's not going to go out enough decimal places to account for those few paper clips that I might have grabbed. So that's why electrons are not included in the mass number. So where are they? Well, the electrons are in the electron cloud. We'll also call them energy levels, orbitals, sublevels, things like that. And the protons and neutrons are both within the nucleus. So first, let's talk about electrons. So in 1897, the English physicist J.J. Thomson discovered the electron. Electrons are negatively charged subatomic particles. The charge of an electron is -1.60 times 10 to the -19, and C is coulomb. That is just a unit for charge. And this is called the electronic charge. So even though we say it's -1 and a proton is +1, again, that's kind of relative. The actual coulombic value is this right here. So this would be the charge of an electron. A proton actually has the same charge, but it's positive. For simplicity, like I said, we assign it a charge of -1. Whoop, that should say of, not or. Thomson discovered electrons by studying a cathode ray tube. So a cathode ray tube is a glowing beam that travels from a cathode to an anode. It looks kind of similar to like the long fluorescent bulbs up in the lights at school. Not quite that long though, and slightly different. Okay, so it looks something like this. So what they did was they kind of put a slit so that the beam could be concentrated more almost like a laser, not the same thing, but it's a smaller beam. And then he put a positive plate and a negative plate on either side because he's trying to figure out what is the cathode ray, like what is it made of, why is it lighting up when I pass electricity through this gas. So he noticed that when he did that, the beam would bend towards the positive plate. Well, what attracts to a positive? A negative. And so that's when he determined, hey, there must be some negative particles, and that's where we figured out about electrons. So I'll see if this video will play. It could not. Doesn't look like it wants to play. So we'll just skip it, but it's just a short video showing them putting the charged plates on either side, and you can see when that cathode ray bends. You can always Google a video yourself. Sorry, I thought mine would work. It works in class, it's just not working in this video for some reason. Alright, so protons. Atoms have no net electric charge. They are electrically neutral. So if there are negative particles, then there must also be positive particles. So in 1886, Eugene Goldstein found evidence for positively charged particles when he found rays traveling in the opposite direction of the cathode ray. Okay, so if we know the cathode ray is negative and something's traveling in the opposite direction of a negative particle, then it must have a positive charge. However, in 1911, Ernest Rutherford rediscovered them in his gold foil experiment and named them protons. All right, so depending on what textbook you have, some textbooks credit the proton discovery to Eugene Goldstein, some credit it to Ernest Rutherford. So just be aware that it just depends on what source you're looking at. The electronic charge of a proton, like I said, is the same as the electron, it's just positive. So it's positive 1.6 times 10 to the negative 19 coulombs. Remember, coulombs is just a unit for electric charge, but we assign it positive 1 for simplicity. So neutrons. In 1932, the English physicist James Chadwick confirmed the existence of neutrons. And remember, neutrons are subatomic particles with no charge. It's very common for a lot of people to say it's negative because they want to say protons are positive, neutrons are negative. However, neutrons are neutral. It's the electrons that are negative. So just be careful of that. Alright, so once they started determining some of this stuff, so once we figured out, hey, there's negative particles in here, there's electrons, J.J. Thomson created what we call the plum pudding model of the atom. Alright, so in the plum pudding model shows the electrons dispersed in a large positively charged area. So I always kind of say it's like you have a large positive force field. Like think about like a superhero movie where they can create like a force field. You have a large positive force field, and then you have negative electrons throughout it. So this whole pink area is positive. There's no nucleus. The nucleus had not been discovered yet. And you have electrons throughout. And so they call it plum pudding model because apparently there they eat a lot of plum pudding. But I like to say it's like a chocolate chip cookie, because over here we eat chocolate chip cookies. So the cookie part would all be the positive, and the chocolate chips themselves would be the negative electrons. So there was supposed to be another video. I'll assume it's not going to work. But that's okay. I'll talk about what the video talked about anyway. So that brings us to Rutherford's experiment. That's what that video that we just skipped again was on. So Rutherford decided to test the plum pudding model by shooting alpha particles. Alpha particles are just helium atoms with no electrons. So it's a double positive charge at a thin sheet of gold foil. Because if plum pudding model was correct, the positive areas are just these kind of like force fields or blobs of positive area. The particles should be able to pass through the foil, but deflect or bend slightly because they're going to kind of bend their path because they're passing through another positive area. And of course, positives don't like each other. But because it's just a positive area, not really a particle, it should be able to get through, but it's just going to kind of change its path a little bit by bending. However, many of the alpha particles pass straight through. Like, they pass straight through, no bending. And some of the particles actually hit the gold foil and bounce back. If plum pudding model was accurate, neither of those things should have happened. So this is just a picture of his setup. So he has his source of alpha particles, which are released through radioactive decay. He has his gold foil, and then he has a fluorescent screen. And what it does is when the particles hit the screen, it kind of illuminates a little bit so you can see where the particles are hitting. So if you look, the straight line is the thickest, so most of them pass straight through. Some of them did bend a little bit, and then some of them literally bounced back. And so that was his actual result right there. So Rutherford proposed that since most of them just passed straight through, they didn't hit anything. So he proposed that most of the atom is actually empty space, and that is what we now know as the electron cloud. He concluded that all the positive charge must be concentrated and have a high mass in the middle of the atom. And that's why some of them literally hit and bounce back. They hit an actual particle. They didn't pass through some positive force field. So he called that the nucleus. And then, of course, the nucleus is the tiny core of an atom and is composed of protons and neutrons. So, like I said, because most passed straight through and didn't deflect at all, he determined most of the atom's empty space. And then, because some of them hit and bounced back, he realized it's not like a big positive area. It's a small, concentrated positive mass in the middle, and he called that the nucleus. So he's credited with discovering the nucleus. So this is just an up-close version of what's happening. Okay, so you can see that many pass straight through because they don't come near the nucleus at all. You can see the nucleus in the center. Some of them, they kind of deflected. That means they kind of skimmed the side of the nucleus. And then the ones that actually bounced back, they hit that nucleus dead on and then bounced back from there. Okay, and so all those that just pass straight through, they only pass through the electron cloud. So after that, of course, we had to have a more updated version of the atom, and that's called Rutherford's model. So in the nuclear atom, or in Rutherford's model of the atom, the protons and neutrons are located in the nucleus. The electrons are distributed around the nucleus in the electron cloud, and they occupy most of the volume. So the electrons take up most of the space, but the nucleus has most of the mass. So it's tiny, but it's massive. The electron clouds are huge space, but they don't have much mass at all. All right, so let's knock out this section assessment. So it says, what are the three types of subatomic particles? Well, it's the proton, the neutron, and the electron. Proton, neutron, and the electron. So number 2, how does the Rutherford model describe the structure of the atom? Well, the Rutherford model has the nucleus in the center, the positive nucleus in the center, and the electrons in the electron cloud. If you want to draw a picture instead, most people, they think it's like the Jimmy Neutron atom. So you have your positive nucleus, and then our electrons are just kind of somewhere around. We're not really sure where in his version yet, but we know there's a nucleus. That's the important part. All right, number 3, it says, what are the charges and relative masses of the 3 main subatomic particles? Okay, so this is just verbal, so I'm just going to say it. So a proton has a positive 1 charge and a relative mass of 1. A neutron has a 0 charge and a relative mass of 1. An electron has a negative 1 charge and a relative mass of 1 over 1,840. All right, so number 4, compare Rutherford's expected outcome of the gold foil experiment with the actual outcome. So remember, he expected the alpha particles to pass through and deflect, so kind of pass through and bend in their path. That was his expected outcome. What actually happened was 3 things. Most passed straight through. So most of them went straight through, perfect straight line. Some of them deflected, like he expected. And some of them hit and bounced back. Okay, so he had most passed through, some deflected, some bounced back. All right, so let's move on. So what experimental evidence led Rutherford to conclude that an atom is mostly empty space? Well, remember, the fact that some bounced back made him realize that there's a nucleus. The fact that most of them passed straight through, that's what made him realize it's mostly empty space. So for number 5, you can put most of the alpha particles pass straight through. So that means they didn't hit anything positive at all. And then number 6, how did Rutherford's model of the atom differ from Thomson's plum pudding model? Okay, well, the easiest thing to do would be to draw them. So plum pudding looks like this, a big positive area with negative electrons throughout. Rutherford's model looks like what we just drew. We have a positive nucleus, so there's one of the differences. And then the electrons are taking up all the space. So there's our other difference. All right, so hopefully again that section wasn't too rough. At least in this one we didn't have any math if you're struggling in math. And so in section 4.3 though, we're going to focus more on the parts of the atom, like how many protons does something have? What is an isotope? How do we calculate average atomic mass? Things like that.